You know, we fear the wrong types of weather. You see, if you ask most people what they're most afraid of when it comes to weather, they're probably going to say something like tornadoes or strong straight line winds or lightning or hail, or they might say hurricanes or something like that. But in reality, you know what you should be most afraid of? Wet and icy pavement. Our deadliest forms of weather, heat and flooding, each kill about 100 people a year on average over the last 30 years. But when it comes to wet and icy pavement, from car accidents alone, there are 1.4 million car accidents in the United States each year blamed on wet and icy pavement. That puts in 700,000 injuries and something around 6,000 to 7,000 deaths. So wet and icy pavement. So we're going to talk today about the ice side of this. Now, a few years ago, I was on a trip up to northern Wisconsin in February. And on my drive up there, I knew that I would be driving through a freezing rain band. Now, I was sent this picture of some of the damage that was done in northern Wisconsin right after I drove through it. But this is what it looked like on radar. Now, I've taught you some neat things about radar, but I haven't taught you everything it can do just yet. You see, we know about images like this, right? The radar reflectivity images, where the color coding tells you the intensity of the precipitation. I've also taught you about radial velocity images, but I haven't yet taught you about this type of image. You see, we can use our Doppler radars to actually remotely sense what type of precipitation is falling and color code it. And you see this color up here? That's all ice. So let's talk about the ice storm. Now, I left Champaign and drove to northwestern Wisconsin. And on my drive up, I drove right through this band and through here. Now, what was going on? Well, this is what we had on that day. We had a low pressure center sitting right here in Missouri. And it had a cold front way back here. It had an upper level front right along this precipitation band, so the cold front was actually behind it. We had a warm front extending off in this direction. Now what that meant was we had warm, moist air in the mid-levels of the atmosphere racing up out of the Gulf of Mexico and wrapping in a counterclockwise direction around the low. And that is key to everything you're going to learn in this lecture. It's the layering of the atmosphere. Warm, moist air running up over the top of the colder air that's near the surface. That's the situation that produced an ice storm right in through here. Now, I got some great pictures of ice damage. Now, these are some communication lines that run along railroads. Now, they don't really have these too much anymore, but I just throw this picture in here because it's a great way to illustrate some of the real problems with ice storms. Ice storms are outstanding at knocking out the power. In fact, you want a little bit of an investment tip? Every single year, when we have our first major winter storm that either produces a blizzard or produces an ice storm somewhere east of the Rocky Mountains, you should buy stock in Generac. Generac is a company based out of Wisconsin that produces generators. Whenever there's a major winter storm, their stock price always goes up right before the winter storm because people go out and buy generators. And then it drops right after the storm. So don't hang on to it for too long, but maybe you can ride that little wave in the stock price. Well, anyways, it's because when you put a little coating of ice on a power line like this, it adds an incredible amount of weight. And that's the problem. When ice accumulates on objects, it produces, well, an enormous amount of additional mass. And when it does that, it can just rip a forest to shreds, knock down power lines. In fact, if you're a student of mine here at the University of Illinois, when you come back to campus, take a look out and see if you can find any above ground power lines on the main part of campus. You won't find them. They've buried all of them. And part of that, not the whole reason, but part of that is so that the power's never knocked out by an ice storm. But I want you to remember one number when we're talking about ice storms. It's going to show up right down here in the bottom left. The National Weather Service, that's what NWS stands for there. The National Weather Service considers an ice storm to be severe and therefore issue an ice storm warning if they're forecasting just 1/4 of an inch of ice. It doesn't take much. You put a 1/4 inch glaze of ice on everything, not only does it start to rip branches out of trees, which can fall on power lines and cause problems, but you can't drive on it. It's too slick. And it's amazing to see how even these cars with all-wheel drive, with great traction tires, can't do anything on a 1/4 inch of ice. And that's why I said we fear the wrong types of weather. Because it doesn't matter what you're doing, 1/4 inch of ice, well, that limits the ability for you to grip the ground. And that's why we have 1.4 million car accidents a year blamed on wet and icy pavement. So 1/4 of an inch is all it takes. Now, I want to teach you some neat stuff about ice. Are you ready? I bet all of you learned this when you were very, very young. Ice always melts when the temperatures are above freezing, right? 32 degrees Fahrenheit, that's also 0 degrees Celsius. But let me undo something that you were not properly taught when you were younger. I bet some of you have learned this already, but here's a quick refresher. Liquid water can remain a liquid at temperatures far below freezing. Water doesn't have to freeze the moment its temperature hits 32 Fahrenheit or 0 Celsius. When water has a temperature below freezing, yet is still a liquid, we call it supercooled water. So it's water in its liquid phase with a temperature below 0 degrees Celsius, which is 32 degrees Fahrenheit. Now this is pretty neat. It turns out that water can stay liquid at temperatures all the way down to minus 40 Celsius. And if you remember back to our lecture on temperatures, that's the only time that both the Celsius and Fahrenheit scale cross. So minus 40 Fahrenheit is minus 40 Celsius. Now, what in the world am I talking about here? Well, I'm going to show you a video. I shot this video when my daughter was about 6 months old. I was very much sleep deprived. I put this video on YouTube so that I could show my students. Well, turns out after about 2 years of showing it, we only had amassed about 800 views. Probably 50 of them were me showing my students. The other 750 were my mother showing her friends. And all of a sudden I showed this in class, and one of my students decides to post this on reddit.com and make fun of me because, well, I was very tired when I shot this video. It was very early in the morning, and I made a mistake with the date. But that's not the science part of this. I want you to watch, because what you're seeing right here is I'm holding a plastic bottle of water, and the water on the inside is super cooled. And I want you to watch what happens. Are you ready? Here we go.
All right, so it's 7:30 in the morning on, what is today? January 27th.
Okay, I told you I was tired. It was January, not June or July. Let's keep going. Ready?
And came out to start the car and noticed that even though it is 17 degrees outside, I have a liquid bottle of water in my car. So what I'm hoping is if I can shake this or see if I can just squeeze it, that it will just, there it goes, froze solid just like that.
Now, I hope you're as amazed as I was when I made this video. Watch it again. Let's start right here. Here we go.
Bottle of water in my car. So what I'm hoping is if I can shake this or see if I can just squeeze it, that it will just, there it goes, froze solid just like that.
Now, what in the world is going on here? I hope some of you have seen something like this in the past. Well, what we just did here was we took a bottle that was full of liquid, supercooled water, and we caused it to freeze. Now, what do I want you to know about this? Well, in order to get water to change phase, in order for water vapor to condense to make liquid water, or for liquid water to freeze into ice, it needs help. It doesn't want to do it automatically. In other words, to make a cloud in the atmosphere where we take water vapor and convert it over to liquid water, well, there must be something in the atmosphere for the water vapor to condense upon. We call it CCN, cloud condensation nuclei. It's stuff, impurities, that's a key word here, impurities floating around in the atmosphere. You can see them. You ever seen like a shaft of sunlight coming in through a window and you can see the little floaty particles in the air? Those are really, really, really giant nuclei, big ones. In fact, your nose and your mouth and your throat are actually designed to filter out, well, cloud condensation nuclei. You cannot make a cloud in the atmosphere without impurities. You need them. It's a site onto which to get the water vapor to condense. By the same token, to get water to freeze, it needs something to help it lock into its lattice ice structure. If there's no helper, like an impurity in the side of that plastic bottle, for example, or if there's no object, like at the bottom of like a rough surface in the bottom of an ice cube tray, if there's nothing there to help the water molecules lock into hydrogen bonds to permanently make ice crystals, well, it won't do it. It will spontaneously do it because it loses enough energy by the time we get to minus 40. But that means from 0 degrees Celsius to minus 40 degrees Celsius, it's possible to have liquid water that has a temperature below freezing. By the way, this works in the opposite direction as well. You can superheat water. Now check this video out, which my students made for me and sent to me. Are you ready? It's called Superheated Water Quarters. Here we go.
This is superheated water quarters. Whoa! That's for you, Snodgrass! Science works!
Okay, so love these guys, right? That's for you, Snodgrass. Your science works. All right, it's not my science. It's the basics of how our planet works. Now watch this. So the guy has, so this is actually a jug of distilled water. and he sets it down here in the CAMS glass. Whoops, sorry. Sets it down here in the CAMS glass. There we go. And I want you to watch one little feature. Let me see if I can find it here. Did I miss it? That. See that bubble rising right up there? Now, where did that come from? That bubble came right from here. Have you ever put a pot of water on the stove and tried to boil some water? Do you notice how all the bubbles keep coming from the same spot? Well, that is a little impurity, an imperfection in this glass, and it serves as a site onto which we can get the really, really hot water to vaporize. That's a bubble of water vapor. Now, the moment that the dirty quarter gets bounced off the table and goes into the glass, well, the dirty quarter has so many sites on it for nucleation, the rapid conversion of the liquid water to water vapor, and it just rapidly boils. Now, what's the problem? You may have put this in the microwave to heat up a cup of water for some tea. You put in a spoon to stir it or drop in a tea bag. If the water is super heated, it will instantly boil and can burn you. Got to be careful doing this. Oh, and by the way, Sam Adams understands this. Sam Adams produced a beer a few years ago where they said when you pour this beer, it's perfect to have 1 inch of head on the top. So they designed a glass that had a nice little bulbous end on the top of the glass, and then they etched with a laser in at the bottom of the glass a bunch of little imperfections in the glass. They did that so that it would bubble up a ring of carbon dioxide to produce the head. You see, it's all about getting the water to change phase, and it needs help. Now let's bring this all back to ice storms, okay? In order to make freezing rain, well, liquid water needs help becoming ice. Now this is what ice looks like. Hydrogen bonds. This is where the hydrogen molecules hanging onto the oxygen bond with a nearby oxygen and make this 6-sided lattice structure. That's why our ice crystals tend to grow with 6 sides on them. They grow as fractals. They grow basically around the shape that they are at the molecular level. Okay, so all ice crystals are hexagonal. They have 6 sides to them. They lock into this lattice-like structure, and at the basis of where they lock into this, there's some impurity, an ice nuclei that serves as the site onto which the crystals begin to grow. Without them, they don't do this. They stay liquid. So we need the impurity. We need this thing to make that happen. Now, this is what I want you to get. Ice nuclei, see it right here, are relatively rare. They exist in the atmosphere, but they're not everywhere. And they're typically only effective when the temperature gets below -15. Now, what does all of this mean? Well, the atmosphere is full of all these floaty particles, soots, aerosols, dust, stuff in the atmosphere onto which water vapor can condense or liquid water can freeze, the nuclei, okay? But it turns out to turn water into ice, we got to get pretty cold. Not 0 degrees Celsius, but -15. And therefore, in our atmosphere, if we don't have the ice nuclei, or it's not below -15, we can have liquid water that remains a liquid. And therefore, our atmosphere is full of liquid water that has a temperature below freezing. Supercooled water. Now, what does all this mean for our lecture? Well, that's how we define freezing rain. It's when some of that supercooled water freezes on contact with a surface. And the key difference between freezing rain and sleet is that statement right there. Freezes on contact. Sleet freezes before contact. Sleet doesn't cause 1.4 million car accidents. Freezing rain does, because it freezes on contact and produces a glaze across the surface. Okay, that's our deep kind of science stuff we got to get out of this. If you need to watch it again, watch it again. Here we have a massive winter storm. What have I taught you? Well, the low pressure system is right here. To the south, look at all the thunderstorms. To the east, look at all the heavy rain. Do you see the pink? That's us using radar to tell us where the ice is located. So storms to rain to freezing rain and sleet, and the backside, snow. That's what we're going after, okay? Now, to put it down into a diagram for you, check this out. I'm showing you a 3-front system. So there's a cold front on the backside, there's a dry line to the south, and a warm front east. Now, we don't spend too much time in Atmos 120 discussing fronts, but they're boundaries between air masses. We know that it goes thunderstorms, rain, freezing rain, sleet, snow, heavy snow. So that's our transition of precipitation. You need to make sure that you know that. Now, what's going on? Cold air coming out of Canada here, dry air coming out of the desert southwest and out of the convergent part of the jet stream here, warm, moist air coming over here, and cool, moist air there. Now, did you notice something? My warm, moist air overlaps. And we're going to talk about what happens right there, where the warm, moist air is running up over the top of the cooler and drier air that's to the north of the low. So what happens right here where the star is located? Well, it boils down to understanding the temperature profile of the lower atmosphere. So I have a very simple sounding diagram in the lower right-hand corner. Now, the criteria for the development of freezing rain, you just have to have two things. You need to have your air near the surface be below freezing. You need to have a warm layer, though, trapped above it, which means the temperature profile needs to look like that. Now, what is this? Well, look, there's our surface it's right on the surface, our surface air that's below freezing, and the warm layer above it. It's a sandwich. Look at this. Cold air up here, below freezing. Warm air here, trapped between that and cold air at the bottom. So cold, warm, cold. See it? Below freezing, above freezing, below freezing. Now, what does all this mean? Well, that deep melting layer sitting on top of this shallow surface, that's what SFC stands for, the shallow surface of freezing layer, does this to a snowflake. Are you ready? Here is a cloud, and I'm going to make it produce one snowflake. Now, as the snowflake falls, it's pretty happy until about right there. You see, at that point and above, the temperature's below freezing. Snowflake stays a snowflake. But the moment that it drops into this layer, well, in that layer, well, look at this. The temperature's above freezing. And as it falls, the snowflake melts and eventually melts and turns into a raindrop. Now, what's neat about this is from this point, I've got highlighted right here, to the ground, which we just brought up, the drop continues to fall. But as it falls, it gets back into some air where the temperature is below freezing, but it's not yet to minus 15. And the drop doesn't spend very much time in this. This may only be 500 or 1,000 feet deep. It's not very much. The drop falls through it very quickly. Therefore, instead of refreezing, the snowflake, which melted into a raindrop, supercools and then freezes on contact, producing a glaze of ice on top of things. Freezes on contact. That's what we're talking about here. The symbol, again, is this kind of yin-yang looking symbol. So you got this swervy line with two dots in it. That's the heavy freezing rain symbol. So again, two criteria, a melting layer that's deep and a shallow surface of freezing level. That lets the snowflake completely melt, then super cool before it freezes on contact with the ground. So let's come back to this thing I showed you earlier. Well, the low is here, cold front there, warm front there, and the warm, moist air racing out ahead of it, wrapping over the back. And over the back side of the low where the warm air goes over the top, we've sandwiched cold air near the ground and warm air aloft. Now let me show you how this works. See these two animations? This animation over here on the left is the surface winds. See the warm, moist air coming up like this? Now wherever you see this break over to this color, you're looking at below freezing air. But let's go up 1 mile above our heads over here. Now the warm air extends much, much, much further into Wisconsin. Still see it wraps around the backside of the low like that. But what does this mean? Well, look down here. That line I just drew right there is the freezing line. And here's Illinois, and there's Wisconsin. And I was driving right through here. So the surface of freezing air was there. But aloft, the only freezing air was tucked way back here. And I was on my way to this spot right here in northern Wisconsin. That means 1 mile above the ground, the air temperature was above freezing. On the ground, below freezing. Do you see the sandwich I'm talking about? Above freezing, that's the melting layer. Below freezing, that's the surface shallow subfreezing layer. And I drove right there across that line. See it? So what did I experience? Well, this is what I experienced. The whole way from Illinois, which is here, to the Wisconsin border there, then driving up north to where I was going, looks something like this. There's the cloud cover extending about 4 miles up. Sorry, it's kind of cut off there, about 4 miles up. And here's the warm air, which you saw a few moments ago. Remember, it's this stuff right here, snaking up out of the south. So there it is. Now that color I gave to it tells me that it's above freezing. Now the cloud above was below freezing. It produces snow. I tried to put all these snowflakes in here. And these snowflakes are making it all the way to the ground, way up north. But it's what happens right in here that I want you to learn about. So again, the airflow is just like this from the south to the north, and all the air that you see in here is above freezing. So let's take a look at this box right here, okay? Blow this up. There's the nose of that warm air, and the snow is falling just like this into it, okay? It gets all the way to the ground here, so there's certainly snow that hits here, because outside of that blob, this warm blob, everything I'm kind of circling here, well, that's all below freezing. But what happens to the snow that falls into the warm layer? Well, it melts. But what's interesting is this. Here, as the snow falls in and melts, it doesn't spend very much time in the warm air. And therefore, when these raindrops fall right back outside of that warm layer, they refreeze because they have enough time and it's cold enough to refreeze back into these little dots you see here. And that's called sleet. But right in through here is what I want to talk about. You see, snow is falling. This is a very deep melting layer and a very shallow layer right down here. See the little white kind of carved out? That little layer in there is below freezing. So these droplets don't freeze back into ice, which is what I tried to show you over here with these dots. Instead, they supercool and they freeze on contact. Over here, it just all hits the ground as rain. So watch this, ready? South to north, rain, freezing rain, sleet, snow. Looks exactly like what I just taught you about the extratropical cyclone. Rain, freezing rain, sleet, snow as you go north. And we're going to talk about these two types right here, the difference between freezing rain and sleet. Quickly, let me show you a real live sounding of this. I showed you kind of a generic sounding a few moments ago in the lower levels of the atmosphere. Here's a real one. So there's the freezing line. That's the 0 degree isotherm. So on this side of it, it's above freezing, and on that side, it's below. There's the temperature of the atmosphere. Do you see the melting layer right down here? Look, the temperature goes briefly into this warm pocket before going back toward cooler temperatures near the surface right there. That's the sandwiching effect. Below freezing here, above freezing there, below freezing here. And look, the depth of the melting layer is substantially deeper than the depth of the surface sub-freezing layer. And that's key. That's the difference between sleet and freezing rain. This is a freezing rain sounding. And I got permission from this Twitter user to show this image. This is what actually happened back in 2015 when this sounding was captured in the panhandle of Oklahoma and Texas. They had freezing rain that accumulated. I just want to show you one picture. Look, it accumulated on this sign, and then the ice slid off of it, and you can still see speed limit 25 written on it. I think that's amazing to look at. All right. There's another place in the United States where we get a lot of freezing rain. Let's see how the ingredients come together. That other place is right here along the east coast of the U.S., especially down near the Appalachian Mountains. We call this region the region where we get cold air damming. So there's a big low pressure system right here. Now, what do we know? Air spins counterclockwise around it. But the mountains right in through here, see the mountains? They can often force air to kind of channel from the northeast to the southwest, just like this, into the low. So the mountains are a barrier in through here. Now, why is that substantial? Well, I'm going to show you another set of winds. See these right here? They're a couple miles above the surface. They're not impeded by the mountains. So they just spiral around cold air, that's the blue on the backside, warm air, that's the red on this side. Can you see how right in through here the warm air goes over the top of the cold air, the black air is underneath it? That's why we have a region right in here where we get a lot of cold air damming. Now, when it comes to where we get a lot of ice storms in the United States, it basically stretches from Iowa, Missouri, Illinois, through the Ohio River Valley to the northeastern part of the United States and southeastern Canada. The bullseye is going to be the northeastern United States and southeastern Canada. But we can occasionally get ice storms that snake right down here next to the Appalachian Mountains, and that's what I want you to see. Now watch the ingredients come together. The graphic in the upper right will kind of explain this. There's our mountains. So the Appalachian Mountains are here. The cold air snakes along the mountain slopes, are right there. And then the warm moist air goes over the top of it. That produces a lot of clouds. They make precipitation. But as that rain falls into this pocket of colder air right here, it supercools rather than freezes and produces icing events. In fact, Roanoke, Virginia, which sits right on the Appalachian Mountains, is famous for its freezing rain events. So the rain supercools rather than freezes, and therefore it freezes on contact rather than freezing in the atmosphere. So this is another example of how this works. Let me give you one more example here. Sometimes in the middle of winter, we have these big domes of high air pressure that come down, bringing very cold air along the leading edge, which is where you see this blue dashed line. Now, along that blue dashed line, which is seen right here, see, that's the cold air snaking southward from Canada. We'll see warm, moist air temporarily go right up over the top of it, coming out of the Gulf of Mexico. When that happens, it does something like this. Now, look, do you see the sandwich again? Warm, moist air overrunning cool, dry air. That's the sandwich effect. And right along that area, we get a band of freezing rain. So all of these ways are different ways by which we get it. But you see there's a common theme. A melting layer sitting on top of a freezing layer. That's what makes it happen. Now, what's the difference between freezing rain and ice pellets? Well, the key difference is the depth of the melting layer. Let me show you what I mean. Here is the melting layer of an ice storm and the surface subfreezing layer of an ice storm. Of a sleet storm. Do you see the difference? Now, instead of being really deep, the melting layer is shallow, but the surface subfreezing layer is very deep. So again, this is for sleet or ice pellets, not freezing rain. There's my cloud. There's the snowflake. Snowflake is fine to about right there. This is when it then starts to fall into a melting layer. But the thing is, the melting layer isn't deep, so the snowflake doesn't completely melt. You see how I drew in here that little speck of a snowflake right there? That's because as it begins to melt, some ice stays in the middle. Now, as soon as it falls into this very deep subfreezing layer near the surface, that little ice crystal still sitting in the middle of this melting snowflake helps the whole thing refreeze back into a Dippin' Dot. That's really what it looks like. This is what sleet looks like. And this is so much easier to drive on, these ice pellets, than freezing rain. Now, sleet doesn't bring down trees, and that's because it doesn't accumulate on them. It bounces off. You've probably driven in sleet. It just bounces off your windshield. Or you've walked to classes where it just bounces off the ground or bounces off of you. It's already frozen, therefore it doesn't freeze on contact. And that is what makes the difference between freezing rain and sleet. Freezing rain freezes on contact. It is rain that freezes. Sleet or ice pellets is already frozen. Big, big, big difference. So let's make sure we get all of this, because the difference between freezing rain and sleet is huge. Let's go back to the situation in Wisconsin. Now look at this. What we've got here is our nose of warm air cutting into this cold air. So everywhere on the outside of it, it's below freezing. On the inside of it, where I got this kind of pinkish color, that's where it's above freezing. Now what do we know? Well, we know that out here it's cold enough to support snow. We know that right here we have a very shallow, look at it, it's very, very shallow depth of the melting layer. See that? I'll kind of put an arrow in there. Very, very shallow melting layer. So the snowflake comes in, it tries to completely melt, but then refreezes into these, Dippin' Dots, if you want to call them that, these little ice pellets before hitting the ground. Over here, look at how much deeper the melting layer is. See that? Therefore, the snowflake falls in, completely melts, and then refreezes on contact. And over here, the melting layer extends all the way to the ground. Hence, it never gets a chance to refreeze or freeze on contact. So here is snow, sleet or ice pellets, freezing rain, and rain. Let's test your knowledge on this. Here's a sounding. Now look, here is the freezing layer. The freezing line. So it's above freezing over here, below freezing here. This is the temperature profile of the lower atmosphere. What type of weather would you expect to get if this sounding showed up? Think about it. Well, I hope you're thinking about snow. Do you see how this line, our temperature line, let's label it T, is never once getting on this side of the freezing line? Therefore, the whole thing stays frozen. This is the temperature profile that we get right here in the snow. All right, next one. What do you think this gives you? Now, when I look at this, I see that part of this sounding is certainly above freezing, and part of it down here is definitely below freezing. So I know I'm either going to get sleet or freezing rain. Now, when I look at it, I see this is the surface subfreezing layer, and that is the melting layer, and it is sufficiently deep. Therefore, this is most certainly freezing rain. Deep melting layer, shallow subfreezing layer. All right, that should make the rest of these relatively easy. What do you think we get when we have this? See the difference? Shallow melting layer, deep subfreezing layer. This sounding would happen right here. That would be ice pellets or sleet. And finally, hopefully this last one will just make a lot of sense here. That's rain. Now look at it. The temperature starts off below freezing up here. So let me kind of draw this for you. This part of the sounding is way up here, above freezing. This part of the sounding is down here, above freezing. Therefore, you have below freezing air up here aloft and above freezing air down here. The snowflake melts and the whole thing hits the ground as rain. That's the difference between sleet and freezing rain, snow and rain. Remember, 1.4 million car accidents caused by wet and icy pavement every year. This is, when you think about weather-related killers in the United States, our deadliest form of weather. Now remember, it's weather related. You're not killed directly by the freezing rain. You're killed in your car for driving on it. So therefore, we don't count that as a direct fatality like we can with heat or flooding or lightning or tornadoes. But when it comes to your human livelihood, you got to be on the lookout for wet and icy pavement. So with that, I'll go ahead and wrap up this lecture here on sleet and freezing rain.